Okay, thank you for the introduction. So, big data, volume, velocity, variability, veracity, 4 V's by which it's often described. I'm interested, as per the introduction, in large, unusual data sets of volume, variability, and in particular, image data sets. So I'm interested in discovering or extracting information from image data of all sorts and with respect to many applications. So I'm going to start off talking about the challenge of knowledge discovery in data, then go on to have a look at the motivation behind this presentation, then look at a lot of different example applications from research projects I'm involved in or have been involved in, and then go on to look at how we went about addressing these problems. But we're going to look at the way that we address the problems by tying them all together into sort of a strategy of how we might do that, and then finish off with some conclusions. So we have many, a bit controversial, but we have many established techniques on how to do knowledge discovery in data. Working with industry, it's not the application of the techniques that's the problem, it's the end-to-end process of getting the data into a format where we can apply the knowledge discovery, and at the end, using techniques to visualize what we've actually got, understanding what we've actually got. So the end-to-end KDD process. So I'm interested in the beginning of this, the preparation of the data. In traditional data sets, tabular data sets, this is fairly straightforward. If you start looking at unusual data sets, video, voice, graph, image data, this becomes a lot harder. So I'm going to talk about image data sets, specifically 2D and 3D image data sets, and as you will see, that there are a great variety of different sorts of images we can look at. And I'm particularly going to talk about prediction or classification. So we want to use our image sets to learn something about them, and then to use those image sets to do some predictions with respect to other images, future images, which we have not seen before. On the right-hand side of that slide, I've got an X-ray of a foot. That's one example of the sort of images I'm looking at. There will be many other examples. So one of the important elements of this is preparing our data, and most of our classification prediction algorithms work with something called a feature vector representation, which many people in this room might be familiar with. Essentially what we're doing is we're going to describe each image in terms of a vector of values. And to do that, I'm going to look broadly at 3 different techniques: statistical techniques, point series techniques, and graph-based techniques. So I'll talk a little bit about the motivation, then go on to look at some examples. So decisions are regularly made using graphical information, using images. Especially true in the medical domain, where many of us will be familiar with X-rays at the dentists, having our eyes photographed at the opticians. There are many, many different types of images which we use for making decisions. Typically, that decision-making process is done without any computational computer backup. Experts, as in this slide, we have somebody in the bottom right-hand corner looking at an X-ray, make decisions by visual inspection of images. There's very little computer support. There is some support, and I make reference there to something called Brain Voyager, which is used to help interpret MRI brain scans. but the key word there is help. It doesn't do it for you, it allows you to measure the width, depth of elements in the brain. A quick review of the classification process. So what we need here is labeled training data. Training data that we've obtained from somewhere and has been marked up by domain experts. We translate that into a format, into the feature vector format, so that we can generate a predictor, a classifier of some sort. And then on the bottom half of that slide, we use the classifier to predict the nature of images that we've not seen before. So we have an unlabeled sample coming in there. We then do some data pre-processing. We use the classifier we've generated to label that image. So in a simplest form, we only have to generate the classifier once. So that might require a lot of processing power, but once we've generated it, we can possibly use it out in the field. It's every time we want to update the classifier, we want to go back again and generate it again. So the classification process is the important process in there. And then we've got the application on the bottom of that slide. Okay, I'm going to look at a number of application domains, and I've drawn these from various areas that I'm working in, and I've drawn them because I think that they might be interesting to people in this room. So the first application domain is looking at 2D retina images. These are the sort of images that are taken in opticians but are slightly higher resolution. So they're typically done in hospitals where people have things wrong with their eyes. So we've got three images there. On your left-hand side, that's actually one of my eyes. And I'm quite pleased to say when I did this 5 years ago, there was nothing wrong with it. I've not had a checkup since then. The images on the right are AMD images, age-related macular degeneration. It's something that eventually we're all going to get, we're all going to go blind. That's the good news. The bad news is that there's nothing that can be done about it. So age-related macular degeneration is becoming a problem as the global population is getting older and older. We're living much longer than we used to. And so we can start screening for it. So if you look at those images, the images on the right, it's quite difficult to see that there's very much difference between the image on the left. If you look at the image in the middle, there's some dots in the central area. Those are fatty deposits, which are indicators of age-related macular degeneration. The image on the right has also got some yellow dots towards the right-hand side, another indicator of AMD. So the point is, it's actually quite difficult for a computer to analyze these and differentiate between the two. But we can do this to quite a high degree, 98, we've got 98% accuracy on some occasions, differentiating between these images, although at face value it's not clear. So this is normally done by experts in hospitals, trained clinicians. So this is a 2D image data set. Oops. Here we've got a Google satellite image. We've got some help from Google in London in the UK, and the observation here was that we could collect census data by looking at the content of Google satellite images. We've got a whole pile of them together, several thousand. We could do a census of some area of the globe. It works particularly well in rural areas. This is a part of Ethiopia. As I said earlier on, for our training set, we need to know how many people are living in each house. So we've got 4 houses there, or households, and we had a team in Ethiopia that went round and did a census. They collected an awful lot of data, not just census data, so we knew how many people there were in each house, we knew the latitude and longitude, we could get the Google images, and then we could process these images and do a census collection over an area. And again, we were able to do this with quite a high degree of accuracy. This is work with an Austrian company that writes software for predicting osteoporosis. And again, an age-related thing where your bones become more and more brittle and are more likely to break as you get older. And we have, on the top right there, that's actually an image of the knee. On the lower image, that's close-up of an X-ray of the knee, and you can see that it's a texture map. And by analysing the texture of those images, we can predict osteoporosis or not. So people who are being screened for it, we can take the X-rays and then through a computer mechanism classify them as being osteoporosis or not. And we can do that using a texture analysis mechanism. Texture analysis is a sub-branch of image analysis, if you like, also used with satellite images where, for example, we want to do deforestation studies. Here's a brain scan. We can do, brain scans are used in a lot of medical applications to test for certain conditions. Epilepsy is one of the ones we looked at. We also looked at whether we could detect the difference between left-handed people and right-handed people. And interestingly, we looked at whether we could detect the difference between musicians and non-musicians. We've got 80 musicians from the Liverpool Philharmonic Orchestra, and we've got 80 other people, a control group, who saw that they had no musical ability at all. And we could tell the difference to a very high level of accuracy, 99%, 100%. So what we're looking at here is some of the features in the brain. And in the brain you see a sort of very dark area, black area, those are the ventricles. And just above, on the left-hand image, just above the dark area, there's a white curve, which we'll be getting back to, called the corpus callosum, which connects the left-hand brain to the right-hand brain. And I'm told by clinicians, you can tell a lot from the nature and shape of that. And so we did a lot of analysis on that. And what's interesting about that was that we did the analysis, we had high accuracy, being able to tell the difference between left-handed and right-handed people, musicians and non-musicians, detect epilepsy to a certain level, and we decided that we got 80% accuracy on that. So what we felt was that there was more to detecting epilepsy than simply looking at the corpus callosum and the ventricles. But it's quite interesting that you can do this, and if you look at the individual MRI brain scans, there's no obvious difference between the different scans that you can detect with the human eye. So it's the computer that is able to identify these differences. I've got one more, and hopefully I've got a video to go with this. No, I can't find a mouse. Whoops. Sorry, I'm going to step down. There we go. It's a very short video. This is steel manufacturing. This is a machine that pushes out shapes using a process known as asymmetric incremental sheet metal forming. It was part of a big European project involving Airbus in Toulouse, Tecnalia in the north of Spain. This machine was actually in the north of Spain, many other partners. And what we were looking at here was the distortions that result of the machine pushing out the shape. So the machine has pushed out a shape here using this tool head. The tool head is static in this case, and we move the, in this case it was stainless steel plate round and push out a shape. And what happens is that the shape produced isn't the same as the specified shape because the machine introduces distortions. So we looked at this in terms of a 3D image analysis problem by representing the shape using point clouds, and I'll come to that a bit more later, and predicting what what the distortion would be. And distortion is referred to as springback in the sheet metal forming industry. And if we can predict the springback, we can apply some corrections and build a shape that's taken the springback into account. We don't get a perfect shape, but we certainly get a better shape than we had originally. And these machines are used typically for building high-spec parts for aeroplanes, space research, and typically the parts are made out of titanium, so it's quite an expensive process. Last one is the 3D OCT scan of a retina volume. So the earlier retina volumes we looked at, the 2D ones, the technology we have now allows us to take 3D volumes of retina images. The argument being that looking at something in 3D gives you a lot more information than 2D. Of course, the amount of information has increased exponentially and becomes harder to analyze. And this one is a retina that has got nothing wrong with it. A retina that has got things wrong with it has got sort of bubbles in it and blobs and things that, to even somebody like myself who isn't a clinician, I can see quite obviously that this isn't right. Okay, so what I'm going to talk about now is how we might represent these images. And broadly, what I've done here is thought about the different techniques we've adopted and tried to apply a categorization to this. So I've divided it up at that high level at global representations where we want to look at the entire image, and local images where we want to look just at one part of that image. So on the left-hand side, I've got a retina scan. On the right-hand side, I've got an image where the yellow blob is the bit we want to look at. Looking at the left-hand side, you do this statistically. We can extract statistics from the image, and I'll talk a bit more about these techniques. Or we can represent the image as a graph. Over on the right-hand side, we've got more techniques available to us. We can look at individual segments, or we can look at multiple segments. On the left-hand side there, I've got a Google Map image. On the right-hand side, I've got a bit of one of the shapes that we looked at in the video. And then further down there, I've got different representations: statistical, point series, graph, and again statistical friends. I'm going to look at each of these in a bit more detail. We've got global approaches, local approaches. The thing about local approaches is they require segmentation. You've got to identify the object in the image that we're interested in. Segmentation of images is a whole research field in its own right and outside the scope of this presentation. So we just have to accept that we can do that. And indeed we can. And then the three different techniques. So what's important to note here is that whatever representation we use, it doesn't have to be interpretable by humans. A lot of clinicians in the medical field don't like that. The fact that we're representing their images using lots of noughts and ones that they can't understand. But for the purpose of doing the machine learning, the data discovery, you don't need to have a representation that is understandable by humans. With the rider, that we in some cases want to offer explanations, and that's true in the medical field. So the most important thing there for me is that a lot of the representations don't have to be interpretable by humans. So there's a lot of different things you can play with and experiment with, using different number ideas, different ideas about graphs, different ideas about point series, point clouds. So I'm going to go and have a quick review of the different techniques, starting with the statistical techniques. It's the simplest approach. At its very simplest, all we do is measure the length and width of something. Alternatively, we look at the average color, the average variance of color, but we can get more sophisticated if we look at individual objects. We can look at the curvature, volume, size of those objects. Then we can take first order functions like means, averages, and second order functions where we translate our image into another format and extract statistical information from that. And I've got a few examples there: co-occurrence matrices, gradient analytics, Huff transforms. The statistical technique works well for some applications. Quite often it's quite simple. Other applications it's just not expressive enough. And I've got a bit more detail. So one technique we can use is what are called local binary patterns, where we look at each pixel, look at its neighbors, and derive a binary value for that. Because there are 8 neighbors, this is a byte and a nice computer number. We have 256 different variables which we can then build into a histogram. And once we've got our histogram, one on the left there, same histogram on the right there, we can start applying KDD techniques to classify those images, those histograms. The most common one we can use is one called Coenen. Many people in this room will be familiar with it. We have a database of pre-labeled curves. We try to find the most similar with respect to a new image. The most trivial way of doing that is just Euclidean distance. Each point in the new curve between each point in each curve in the bank. A lot of comparisons going on there, but it requires that our curves are the same length, and again, it's often not expressive enough. So a technique I like using, partly because of what it's called, is dynamic time warping, which sounds very space age. And essentially what you're doing is you're allowing for variance in the time series. And it has the additional advantage it can be used for curves that are different lengths. So we can use histograms of local binary patterns to generate curves. For objects, this is slightly more difficult. So what we want to do is generate curves that represent individual objects. I've got one trivial technique is chain coding, where we simply go round the edge of the object. It assumes it's been segmented, and then pick up where each pixel is and use a coding for that. And the coding I've given there is that the next pixel is to the north, the code is a 1, if it's to the northeast, the code is a 2, and so on, and we can produce a feature vector from that. Here we have some other techniques. This is a ventricle extracted out of an MRI, 3D MRI brain scan, and we've used a disk-based technique and a spoke-based technique to trace round the edges and to produce point series, which we can then represent as curves. Here we have another example with the corpus callosum. In the image on the right-hand side there, we have a dark blob in the middle there, surrounding the corpus callosum, and again, we can generate point series from that. This is 2D by taking spokes out from a point and producing a curve, and that works well. There's the corpus callosum. Moving forward, we've talked about statistical techniques, we've talked about point series techniques. This is the graph-based techniques. Graphs, quadtrees, are a very popular mechanism for representing 2D images. They've been used a lot in the image retrieval world, image analysis world. We can do this in 2D or 3D. Of course, in 3D it becomes an octree. Few issues with it, that we divide our image up into a grid, we build our quadtree. I'll give an example of this in a minute. We may have features that are on the boundaries between grid cells, which causes us a problem. It's also when to stop the decomposition. and you can go down as far as the pixel level, but as you go down, the complexity of any algorithms you apply increases, so you've got to stop somewhere, and there's various techniques for doing that, called critical functions, and where to stop the decomposition. Here's an example, 2D, corpus callosum. Top left-hand drawing is my drawing. It may very well not be very accurate because I made it up, but you get the idea. So we've got the yellow blob there, which is the corpus callosum. We segment it out, we apply our grid, and then on the bottom right there, we've got our quad tree representation, which is a representation of the original corpus callosum, and we can do the same in 3D. Here's an example using the Retina data we had earlier, where we divide we decompose the retina in this sort of circular manner, focusing, keep decomposing until we get to a certain level and where we have homogeneous segments. Here's another example. This is an OCT. The OCT retina scans are long, thin rectangles. So when we're decomposing, there's a danger that we get down to 1 pixel slices. So we did this slightly differently and included an extra box in the middle. And that partly gets around our boundary problem with the cells. Once we've got our graphs, we need to get these into a feature vector representation. So the idea here that we proposed was to apply a technique called frequent subgraph mining, where we find all the frequently occurring subgraphs in our trees, our quad trees, our oct trees, and then we use those to define a feature space. We can count how many times each frequent subgraph appears, and then generate our feature vectors from that and apply the same techniques that we applied before. So what we're doing here is adding an extra step. We have our labeled training data, we process it to generate graphs. We then use frequent subgraph mining to generate a feature space. So that's one KDD technique. And then we use another KDD technique to generate our classifiers. And the classifiers are then used to sample new data, which of course has to be translated into a graph representation as well to get feature vectors out of that. Okay, so I've talked about a number of different applications. I've talked about a number of different representations. I'm going to talk very briefly about evaluation. I'm not going to give tables of numbers. I have got those if somebody wants the proofs. But broadly, we can extract, make some observations from these results. We found, and this is just the medical ones, we found that for the 2D retina images, our graph-based technique, where we had that circular decomposition, worked very well, got very good results. I've got, afterwards, if there's time, I might tell you about quite an amusing story about how we got the control group for that, because people only go to the hospital to have their eyes looked at. They think there's something wrong with them. So getting a control group was quite an interesting exercise. With the MRI scans, we found that the point series technique worked well in 2D, but when we moved up to 3D, the graph-based worked well. And then using the OCT retina data, the statistics work well. So the message here is that there is no best representation, in the same way that there is no best prediction algorithm, which is sort of annoying. So given a problem, we need to experiment with different representations, different algorithms to find the best solution. So moving forward to a conclusion, looked at a number of application domains from which I think you'll be able to extrapolate further application domains. Looked at some representations which I categorized into statistical, point series and curve-based. evaluated these using some medical domains, and bad news is that there's no best representation. But what I hope I've done is given a flavour of the sort of things you can do in the big data world, analysing images, getting information out of those images, using that information to create classifiers, predictors, which can then be used in a wide variety of areas, such as sheet steel manufacture, census data prediction from satellite images, lots of medical domains. And I just want to finish off with 2 more slides. There's lots and lots of applications out there that merit looking at. So I've got mammograms there, I've got a dental x-ray. I've never looked at that. The one on the right, a colleague of mine is looking at that to predict the age of hands, and it's to do with investigations of child development, whether they are developing, their bone structure is developing the way they should be. I'm not involved with that, but it's an interesting application area. And I just felt I had to acknowledge all the people I worked with. You can see that they're from all over the place. Many of them are in Liverpool, but they're in Thailand, Egypt, Malaysia, Jordan, and a lot of the algorithms and the programming was done with the help of these guys. Okay, thank you very much. I hope you found that interesting.